In this video, we're going to talk about suggested homework problems in Chapter 10, Section 2. We've skipped Chapter 10, Section 1 because it is a review of topics that we covered already in pre-calculus. Go ahead and reread that for yourself if you would like to review conic sections in rectangular form, but we're going to jump right into parametric representations of plane curves. So topic today is plane curves and parametric equations. Let's go ahead and ask the first question here. What information does a set of parametric equations provide that is lacking in rectangular equation form for describing the motion of an object? We are able to get the position, direction, and speed of the object at a particular time. Parametric equations don't have to necessarily have their parameter represent time. If they do, time has to be greater than or equal to 0, since we can't travel back in time unless our problem is specifically asking us to project what happened back in the past. In that case, we could start off with an initial time of 0 and say we want to look back 50 years into the past or 100 years into the past or something, and there would be some sort of meaning to a negative time value. But typically we start at initial time is 0 and move forward with time. So just be aware of that contextually as we read problems, that you're typically not going to have negative time values. All right. How can two sets of parametric equations represent the same graph but different curves? So several different options here. The book is going to give you one possible answer here, but we could start off at a different position and a different initial position. So different initial positions, everything else the same. We could be traveling along the same path at different speeds. We could be traveling the same path but in opposite directions. So we could be mapping out all the same points, but we could be doing it by starting at a different position or traveling at a different speed or traveling in a different direction, or all of those things all combined. So let's go ahead and look at 7. 7 says x is equal to t plus 1, y is equal to t squared. We'd like to sketch the curve of the parametric representation, indicate the orientation of the curve, write the corresponding rectangular equations by eliminating the parameters. So I'll do the last part first here. If I solve for t in the first equation, t is equal to x minus 1. Then y will be equal to x minus 1 squared. Let's see, y has to be greater than or equal to 0 here. X can be anything. as long as t can be anything. So that matches with the domain and range and rectangular form. Sometimes you need to restrict the rectangular form based off of restrictions that you see from the parametric form. So this curve sits on 1, 0 because it's a parabola that's been shifted 1 to the right. I go right 1, I go up 1, I go left 1, I also go up 1, go right 2, up 4, 3, 4, and then another one up. So this should be like this. Now this is all that I would get out of rectangular would be this shape of the graph. And I want to indicate orientation here. So X is moving left to right on this graph. So I'm going to add some arrows like this as time progresses. The particle, the object is moving from left to right on the graph. That shows positive orientation there. As t increases, the particle is traveling along the path in this direction. Let's go ahead and look at number 17. Seventeen says x is equal to e to the t, y is equal to e to the 3t plus 1. So x has to be greater than 0, can't be equal to 0 here. Y is going to have to be greater than 1. It can't be equal to 1 since exponential functions can get close to 0 but never get there. Y is equal to e to the t to the 3rd power plus 1. So y is equal to x cubed plus 1. And when x equals 0, y would be getting close to 1. It doesn't ever get there. And then we're going to have a cubic function. So 1, 2, 2, 3, 4, 5, 6, 7, 8, 9. And it's just this right-hand side here. And my orientation is going to be in this direction. Okay. Let's go ahead and look at 41. Forty-one says that we have an ellipse given x is equal to h plus a cosine of theta, and y is equal to k plus b sine of theta as our parametric equations. In terms of theta, we want to write the standard form of these equations in the rectangular form. So I'm going to solve for cosine of theta and sine of theta and use my Pythagorean identity to make a substitution. X minus h over a is equal to cosine of theta. Y minus k over b is equal to sine theta. And I want the x part first, so cosine squared theta plus sine squared theta is going to be equal to 1. So x minus h squared over a squared plus y minus k squared over b squared is equal to 1. So let's look at 45. 45 tells us to use these parametric equations above as guidelines for a circle, the center at 1, 1, and a radius of 2. And the parametric equations that were given to us were right there with number 40. Let x equal to h plus r cosine of theta, and y equal to k plus r sine of theta. So x will be equal to h is 1, r is 2, y is equal to k is 1, r is 2, and we're done with 45. Now we're going to look at number 49 and show you that you need to make a slight adjustment to the form that was given to us for the hyperbola above. So vertices at 0 plus or minus 1, and foci at 0 plus or minus root 5. All right, so if we look at the hyperbola up here, this hyperbola is opening left or right, and so I need to make an adjustment here for this one to say that I need x to be equal to h plus plus b tangent theta, and y to be equal to k plus a secant theta here, because the a is the distance to a vertex and the vertices are in the y direction here, that the secant theta, the a secant theta piece goes with y, and the b tangent theta piece is going to go with x this time. Just a little bit of an adjustment from what we saw here with the hyperbola set up for 42, which had the hyperbola pieces opening left and right. So let's go ahead and do a little pre-calculus here to say that the center halfway between the vertices is at 0, 0. And we have a squared plus b squared is equal to c squared. A is equal to 1, the distance from the center to the vertex. C is the distance from the center to the foci is root 5. So a squared is 1, b squared is b squared, c squared is 5, b squared is 4, b is equal to 2. So x is equal to h is 0, b is 2, tan theta, and y is equal to k is 0, a is 1, so y is just secant theta. And that's it for this video. We'll come back next time to talk about suggested homework problems from 10.3, which will cover parametric equations and calculus. So see you for the next video.